So, Slava, I think you are there, right?
Yes, but I have now to find the way. Okay, good. Share screen.
Yeah. So
now you see my screen, right?
Yes. Now we see you, and now we see your screen. Okay. So, Professor Mukhanov will talk with us about what remains after black holes.
Okay, good. So let me, first of all...
I will warn you after 20 minutes. That is 5 minutes.
I have half an hour. Okay, good. So now, as you see, okay, this is a work which is done in collaboration with Shamsidin and Tobias Roos. And let me start with brief historical introduction. Because everybody speaks about non-perturbative quantum gravity, but the main question, why do we need it? No, besides blah, 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 like we need two consistent theory, is perhaps the question about singularities and the questions about the final stage of evaporating black hole. And of course, there is not too much done during last, I don't know how many years, on the way of creating this non-perturbative quantum gravity. Therefore, I will use a different approach. I will discuss, do we need really this non-perturbative quantum gravity, or we can change general relativity at very high curvatures in such a way that we will always remain classical, except, for instance, more low energies when you can use perturbative quantum gravity, for instance, to explain CMB fluctuations. But when we go to the Planckian scale, nobody knows what is there. And as you understand, general relativity is also not testament. In fact, non-perturbative general relativity was basically, in fact, checked only recently with CMB observations. Before that, it was a common belief. And of course, a lot of people are speaking about modifying of general relativity. And there are two ways to modify general relativity. Either to add some kind of mess to Einstein equation, or to remove something from Einstein equations. And in fact, actually, several years ago, together with Shamsidin, we found the way that what can we do? We can take in the Einstein action some auxiliary variable and lose the trace of Einstein equations. As a result of losing the trace of Einstein equations in general relativity, there appears two extra components. One thing is cosmological constant becomes a constant of integration. This is actually the idea which goes back to this unimodular gravity. Then Heno and Teitelboim wrote how to do it in the Hamiltonian and corresponding Lagrangian formalism. And we found the other way, or the other consequence of this losing trace of the gravity, namely, this leads to the thing that longitudinal degree of freedom of gravity becomes dynamical. And moreover, this extra degree of freedom mimics the dust in our universe. Therefore, perhaps we can describe cold dark matter even without particles, because it will be just solution, extra solution of Einstein equation with extra constant of integration, which describe the motions of the effective dust without vorticity. And in fact, all these ideas basically can be reduced to the following simple action. If I will forget about origin of the whole modification, then I can take Einstein action and add some constraint to this action where phi is so-called scalar field. But it's not real scalar field because it's not degree of freedom of scalar field itself. It just corresponds to half of the degree of freedom for the scalar field, because this scalar phi satisfies the following constraint, which you get when you vary with respect to Lagrange multiplier. And as you see, it's the first order equation. So it would correspond to half degree of freedom. And this half degree of freedom combined with the other half degree of freedom for the longitudinal mode of gravity gives us dust-like behavior. Now, these kind of things can be investigated very easily in synchronous coordinate system where metric takes this form. You see where d squared is equal to dt squared minus special part of the metric. And the solution of this equation in this coordinate system is just very simple. Phi plays the role of time which numerate hypersurfaces of constant time. But then this scalar allows us to play with it and to introduce something what was in fact very difficult to do when we were modifying Einstein action with higher order curvature invariants to resolve the problem of singularity, because all higher order curvature invariants include at least second derivative, okay, over the time, and therefore you are getting some kind of complications, both whatsoever. But now, if you use scalar phi, mimetic field, so-called, then you can do nice thing out of it, because if you are working in synchronous coordinate system, then you can find out that extrinsic curvature of hypersurfaces time is equal constant is nothing more than just second derivative of this scalar. You see? And for instance, Laplacian of scalar field becomes just time derivative of logarithm of the square root of the determinant of the metric. And so we, in synchronous coordinate system, introduce this kind of first derivative of the metric, which, by the way, do not disappear. And in the other coordinate system, they become very complicated. But in synchronous coordinate system, it's the first time derivative. And therefore, we can proceed with this first time derivative to build, to modify Einstein gravity in the minimal possible way with the purpose to resolve the problem of singularity. There are different kinds of modification, and in fact, it happens that solution of singularity problem in this case becomes very, very easy, nearly trivial, because in the 80s, when people were thinking about solving singularity problem, they were thinking about two ideas. One idea was the idea of limiting curvature, invented by Markov. Rosen also wrote something about it when, in principle, instead of singularity, you have bounds within very, very short time, which effectively, without reaching Planckian curvature or without reaching this limiting curvature, which was happening because effectively there appeared some kind of component in the Einstein equations, which would correspond, if you would interpret Einstein equation of everything, what comes extra in the Einstein equation as the right-hand side, T mu for hydrodynamical fluid, okay, this kind of component had effective equation of state when pressure was becoming negative and practically unbounded. Then you can bounce from singularity very fast. And in fact, actually, we showed that you can do it here, not only for the isotropic universe, but also for the case when you have an isotropic universe. Also, when you apply this method inside black holes, then you see that you can get very complicated structure in this case. For the black hole becomes like Russian doll. When you fall inside black holes and instead of going to the singularity, you find yourself behind of some other horizon of smaller black holes, then further you will find yourself behind of the horizon of even smaller black hole, etc., etc., etc. But we were not able to proceed there to the end because finally all the methods which we used actually, I mean, these perturbation methods failed, and we are not sure what would happen. Singularity would survive or not survive in this case. The other approach is to have, instead of limiting curvature, or better to say, when we are reaching limiting curvature, some kind of space with extra symmetry, namely de Sitter space. And in fact, if you will take these papers by Starobinsky from 78 in about m squared phi squared theory, I mean scalar field, or about r squared gravity, his purpose was to avoid singularity using de Sitter solution. The beginning was, in fact, the main purpose. And then, together with Markov in 82, we had some kind of idea that maybe really, okay, we should not bounce during short time interval, having instead of singularity, but what can we do? Instead of going to the singularity, we can go to the Sitter stage, and we guess that it can be the consequence of the asymptotic freedom of the gravity, when gravitational constant is vanishing when we are approaching some kind of limiting energy density or limiting curvature. But the whole thing was not, in fact, okay, there was several papers which we wrote, also with Frolov about avoiding singularity in the black hole, but there were some kind of models. There was no real theory behind of these models. So it means that there was no equations which you could solve without making some kind of extra assumption. Like, for instance, in black hole, we were assuming that there is some kind of layer which allows us to continuously match metric of de Sitter and thin shell, yeah, metric of de Sitter and metric of the black hole. But within this mimetic gravity idea, it became possible to build very simple model where we can calculate everything, where we do not face with the problem of non-perturbative quantum gravity because we take this kind of limiting curvature, which is the parameter of the theory, much below than the Planckian value, and therefore we have the things under full control. And also we can show, as you will see later, that, for instance, quantum fluctuation becomes less and less relevant when you are approaching limiting curvature. And instead of having this kind of very, very, I would say, very, very wild picture of the, according to Pomeranchuk, which was the boiling liquid of operators, you are getting, instead of this kind of non-perturbative quantum gravity at very high curvatures, below than Planck curvature, again, fully classical theory. So you see, it's the opposite approach. Now, what is the main idea? So let's take, okay, and modify Einstein action in the following way. Let's put in front of the Lagrangian, Einstein-Lagrangian, okay, the term, which would be the function of the Laplacian of phi. So it's covariant thing which only in synchronous coordinate system is reducing to the first time derivative of logarithm of three-dimensional part of the metric in synchronous coordinate system. Otherwise, much more complicated thing. Now, also, we could add some kind of invariant, which depends on this thing. And of course, you are adding standard part here, which corresponds to the extra constant of integration, which can mimic Koldak method. Then, effective gravitational constant, in this case, become the function of this extrinsic curvature in synchronous coordinate system, as you see. And we can claim that there is some kind of asymptotic freedom in the sense that gravitational constant is vanishing when this Laplacian or extrinsic curvature goes to the limiting value, And thus, we can realize the idea of asymptotic freedom in the gravity, in Einstein gravity, by modifying this Einstein gravity, but only at very high curvatures, which are a little bit below than the Planckian value, but above the scales, okay, when you generate cosmological perturbations from quantum fluctuations. You see, and let's look what will be the consequences of this kind of asymptotic freedom implemented using mimetic gravity for the cosmological solution and for the black hole. Now, let's first consider very simple case, Friedman universe, and we will assume that gravitational constant is vanishing when curvature goes to some k0, which is limiting curvature, and this means that the function f is blowing up. So you see, gravitational constant is inversely proportional to the function f, and function f has some kind of simple pole at limiting curvature. Then let's take Friedman universe and let's look how Friedman equations are modified in this case. And then you see that Friedman equation, 0, Einstein equation, which is here 1/3 k squared, and k squared is just 3 multiplied by Hubble constant, which is equal to the energy density. Of course, at low curvatures, we work in Planck units, okay? Is multiplied by this extra factor, which modify Friedman equation only when k, or Hubble constant, starts to approach the value which would correspond to the limiting curvature. You see that here in denominator, the whole thing is blowing up. As a result of this modification, which is in this red square, what we are getting? We are getting the following solution. If we will put here some kind of hydrodynamical fluid with equation of state, pressure is equal W energy density, then solving this equation, we will find that for at the curvatures much less than this limiting curvature, scale factor behaves like in usual theory, Einstein theory. So, for instance, when W is equal 0 and when we have dust-dominated universe, scale factor is proportional to the time in power 2/3. For radiation-dominated universe, it's square root of time. But when curvature, when universe is contracting, and curvature starts to approach the limiting curvature characterized by this k0, this solution, which would run into the singularity, smoothly starts to go to the de Sitter solution with constant curvature. And this is so-called contracting de Sitter, but because de Sitter is time translation invariant, as you understand, you can introduce the other coordinate system, and then you are getting expanding de Sitter. And therefore, in this approach, you are getting cyclic universe. You are getting cyclic universe, which pass through all these de Sitter stages. Okay, instead of going to the singularity, it bounced on de Sitter where gravity acts like anti-gravity, and then start expansion again. But for instance, for the isotropic universe, I think it's Brandenberger in 92, we managed to modify the things in such a way that at least for the isotropic universe, we were able to get bounce, de Sitter bounce. Much more difficult problem was to resolve singularity, which is anisotropic, because it's real singularity, and in fact, actually, this method which we were applying was impossible to implement actually in the case when Weyl tensor is not equal to 0. But in this particular case, when we use mimetic gravity, again, simple modification, which implements the idea of asymptotic freedom, resolve easily singularity in the Kazner universe. Kazner universe, as you understand, or maybe as you know, is anisotropic universe. It's one of the particular cases of Bianchi type universes, which has flat hypersurfaces of constant time, and it's described by the metric, which has this kind of form. So in front of dx squared stands t in power 2p1, then in front of dy squared t in power 2p2, etc. But this p1, p2 so-called Kazner exponents satisfy the following relations, you see. And by the way, also, if you will take the behavior of the metric in the vicinity of singularity in the black hole, inside black hole, you will find that it also corresponds to Kazner universe asymptotically when you are approaching singularity with all these Kazner exponents. So then, if you will consider this Kazner anisotropic universe where you do not need even to put matter, but if you put matter, nothing will change, in fact, because gravitation constant goes to 0, and also curvature terms normally dominate in growth over the terms which are like energy density of the matter. So then you will find, within these equations, which I showed you, that as the curvature is much less than the limiting curvature, you have normal solution like in Einstein theory, but when curvature starts to approach this limiting curvature, again, this anisotropic contraction becomes isotropic, and Kazner universe goes to contracting the Sitter universe where all curvature invariants are constant. You see this kind of behavior. So you see, in cosmological cases, for flat universe and for Kazner, we are solving singularity problem in a very, very easy way. We are getting solution, which instead of going to the singularity, turn to the theta. Of course, flat, especially flat universe, where I showed formulas here, and Kazner universe, which has flat hypersurfaces of time equal constant, are special cases. But as we have shown in the other paper, the whole thing can be generalized. The things becomes a little bit more complicated, but it's not so principal question can be generalized for the case of closed universes, which is very easy, and for the case of other type of Bianchi models. But the main purpose of my talk is to see what will happen with the black hole singularity and what will happen with the remnant of the black hole when it evaporates thanks to Hawking radiation. And for that, I need only solution for the flat, for the spaces with flat special hypersurface in synchronous coordinate system. So
I have 4 minutes left. You have 4 minutes left.
4 minutes left. Okay, good. No problem. So, no, but before I want to make also one remark about quantum fluctuations. If I will take, for instance, gravitational waves, then you know that the amplitude of quantum fluctuations in scale L, is proportional to the effective gravitational constant, which depends on this extrinsic curvature divided by L, and it's clear that when I am approaching this kind of limiting curvature background, then in this particular case, amplitude of quantum fluctuation vanishes. And surprisingly, at very high curvatures, I am getting perfectly flat solution where quantum fluctuations are vanishing. Now, let's go to the black hole. And anyways, the formulas are a little bit messy. And therefore, Therefore, I just show you the basic idea. So let's take the metric for the black hole or for de Sitter. You know that in so-called static coordinate, which of course do not cover the whole space, the metric can be written in this kind of form in both cases, for black holes and for de Sitter. You see, just function R, which is a function of so-called radius, are different for de Sitter and for black hole. To cover the whole space in both cases, and then actually to perform calculation, for us, it's more convenient to go to so-called Lemaitre coordinates, which you can find in Landau-Lifshitz, where he, in fact, investigates the behavior of the black hole in these Lemaitre coordinates, where metric in both cases takes similar form, you see, but where x is a combination of time and radial coordinates. And now we can take this ansatz for the metric, okay, and substitute it in the modified Einstein equations, and then we will get the following result. For black hole, metric becomes like this one, and you see these coordinates are regular at the horizon, which is located at x3 for m/3, and also de Sitter in these coordinates, okay, takes the following form, and the region x smaller than x minus covers the static patch of size h-1, yeah, of the de Sitter. Now, let's take, these are two asymptotic solutions, but when we will substitute this generic metric back, you see, this generic metric back to our modified equation, then we can solve them, and we are getting the following solution for the metric in modified theory, where we will take function f, which is inverse gravitational constant, in this form, because in this case we can solve equations exactly. The only thing which is relevant here is here, but then we are getting exact solution where, okay, metric for the black hole gets like this one. You see, when x goes to infinity, at low curvatures, we have black hole. But when x goes to minus infinity, this solution for the function a and b gives us static de Sitter patch. As a result, we are getting the following structure for the space, which will be modified. If I would take eternal black hole, then here I have the horizons which correspond to black hole horizon, de Sitter horizon, black hole horizon, de Sitter horizon, etc. So it reminds perhaps you the conformal diagram for Reissner-Nordstrom solution, but we don't have here any singularities, even time-like singularities. If I will take, for instance, now mass, which is equal precisely to this critical mass, then I am getting somehow smallest black hole, because for masses smaller than this minimal mass, the conformal diagram is like this one, no horizons, and solution is like solitonic solution, okay, without horizons. Now, let's investigate in this case, when we modify this gravity, what will happen with the temperature of evaporating black hole, which is described by this solution. Okay, for that we have to calculate surface gravity. By the way, also near black hole horizon for minimal mass, like extremal black hole. I'm finishing, yeah. Now, let's calculate surface gravity. And then what we will find this explicit formula, again, parameterizing temperature expressed through some parameter and mass expressed through some parameter, but we can draw what is going on with evaporating black hole. And then we see that at the beginning, when mass is very large, temperature is growing according to Hawking, but then when mass becomes just 30% more than this minimal mass, then temperature drops, and then it vanishes at the point when m is equal mc. and the remnant becomes stable. So what kind of picture we are getting? We are getting the picture when we have the pieces of de Sitter space, roughly speaking, patches of de Sitter space, which are covered black hole horizon, which are flying, can fly in our space and can be stable. In this case, we are getting stable remnant for the black hole, okay, the mass of which is characterized by these three parameters of the theory. Then, okay, all kind of information paradoxes also disappears, and then you do not need any kind of non-perturbative quantum gravity to resolve all these problems. So thank you very much, because my time is over. Thanks.
Okay.
Zurab, are you still awake?
Yes. So if there are questions.
What did you say the mass of the remnant was?
Can you repeat?
What is the mass of the remnant?
The mass of the remnant is determined by the limiting curvature. If you would take Planck curvature as limiting curvature, then you would get Planckian mass. But as I told you, to be on safe side, you can work a little bit below, for instance, order of magnitude below Planckian scale, just to be sure in all calculation also concerning perturbations in this theory. So mass of the black hole is a free parameter which is restricted only by observations. It should be for sure larger than the scale corresponding to 1013 GeV, because, okay, 1013 GeV we checked with observations that gravity there is normal Einstein gravity all the way, because all the result of CMB observations are in perfect agreement with what was predicted.
All right, thank you.
Slava, phenomenologically, how massive you can make these remnants?
Remnants not much more heavy, like 10 minus 4 gram, okay? It has nothing to do with primordial black holes. But, okay, they also can give you the other candidate for the cold dark matter. But although you can mimic this candidate even within this mimetic gravity.
Well, difficult because we are losing mass constantly, so you don't have this amount of the 10 to minus 4 grams, I imagine, right? You have to produce a lot of black holes.
These remnants are stable.
Yeah, but the initial amount of black holes should be. It's what you get after.
I didn't get the point. So can you repeat the
initial mass was much bigger, right?
Yes.
Of black hole, and you are getting at the end 10 to the minus 4 grams.
Yes.
Per each black hole, you are getting 10 to the minus 4 grams. So you
as a
cannot
result
get it.
of Hawking evaporation. It's only for the mass.
But then what should be initial amount of the black hole masses in overall, in order that after the evaporation you will get 30% of the mass of the universe.
You don't need to make immediately very large black holes. You can make black holes which are just a little bit above this thing, as you understand.
No, I understand.
Lose a lot of mass.
Special spectrum is that case for the black hole formation, in addition.
Yes, but you understand that actually to form black hole, primordial black hole, you have to damage a lot the spectrum of the perturbations, which was proven in CMB observations. Of course, you should do it in the region which was not checked by observations, but nevertheless, if you are speaking about primordial black hole, you have to make something very drastic, as you understand, after inflation or on inflation. But to make primordial black hole in successfully verified theory, okay, with observations, you cannot do it because, as you understand, the spectrum there is rather smooth, so you have to make pipes or whatsoever. Here the question is rather academic question also, because there is always all these questions about singularity, about remnant of the black holes, but you see that in principle, it's not even so big headache to resolve all these things. I am sorry that I was not so smart 40 years ago, but maybe then I lost any interest to the whole thing, you know. Okay.
So
Well,
thank you, Slava.
Yeah, well,
We are a little bit late in time. But,
yes, go ahead, but how I can...
Next speaker is Daniele Gregoris about curvature, invariants, and black hole horizons.
Hello, can you see my panel?
Yeah, you can switch.
Can you see my presentation?
Yes. Yes, we can see. You can continue.
Yes.
Okay. I am Daniele Gregoris, and I will now propose a connection between curvature invariants and black hole horizons. My research is supported by China Postdoctoral Science Foundation and by the 2020 Galaxy Travel Award, where Galaxies is an open access journal by NDPI. Black holes are one of the most amazing predictions by general relativity. They deal with small-scale physics because their accretion disk happen to be on scale.
Your share screen disappeared, I think.
I'm sorry?
Your text disappeared, I think.
Can you see it now?
No.
Can you see it now?
No.
One
Yes,
more.
now yes.
Okay.
Now yes.
Okay. So intuitively, black holes can be defined as regions from nothing can escape. And their first was just taken last year, thanks to the Event Horizon Telescope. And the word horizon is one of my thoughts. The presence of an event horizon is a very convenient proposal to protect the predictability of general relativity, according to the cosmic censorship conjecture, because they can hide curvature singularity. Indeed, the space-times with a singularity are geodesically incomplete. However, there are at least two conceptual and one practical problems when dealing with the black hole horizon. In fact, general relativity is a local field theory by construction. However, the book by Ward clearly explains that it is necessary to know the entire space-time evolution for claiming if a black hole is present or not there. And treating black holes as regions from which a light ray can never escape back to spatial infinity is a non-local procedure. Moreover, the book Gravitation by Nisner, Thorne, and Wheeler speaks about global properties of black hole spacetime. And according to this book, for locating the horizon, we must follow the propagation of light rays, and we need to solve the differential Berezhiani equation. Then, from the practical point of view, binary black hole systems are simulated for extracting gravitational wave spectra in numerical relativity. And in this case, it is important to check whether the two horizons should not be mapping. But locating the horizon by solving the Berezhiani differential equation is a very computationally expensive procedure. Furthermore, numerical relativity codes also need to excise the region inside the horizon, because what happened there cannot influence the evolution of what happened outside. And this follows very easily by the definition of black hole horizon as a causal boundary. So the question that we wanted to answer is what is the most convenient way for finding this reason to excise? And in particular, if we can find it by solving an algebraic equation instead of a differential equation. The first speculative answer was yes, at least for the Kerr black hole, because it was noticed that some curvature quantities vanish on the horizon. This first speculation then was promoted into a rigorous mathematical theorem, according to which, under certain hypotheses, it is always possible to construct an appropriate scalar polynomial curvature invariant which detects the killing horizon of a stationary black hole. However, it is important to appreciate and to understand that this theorem just guarantees the existence of this appropriate curvature quantity, but it does not provide any constructive algorithm for actually finding it. Furthermore, it is possible to relate the curvature quantities into the parameters of a black hole solutions, providing a local way of measuring. So here I'm showing what scalar polynomial curvature quantities actually look like. So, for example, you can take the Weil tensor and contract it with itself, or you can contract it with its dual, or you can repeat the same operation with its covariant derivatives, or even replacing the Weil curvature with the Riemann curvature. So potentially, you can construct an infinite tower of scalar polynomial curvature invariants. In particular, you can see that these quantities are, let's say, second-degree quantities because we are taking some square. Here, I'm showing you which is the appropriate scalar polynomial invariant which detects the horizon for the Kerr-Newman not anti-de Sitter metric. You can see that it is a quite involved and complicated expression in terms of these basic pieces. And we could identify it only playing by hands with these basic ingredients with a trial and error procedure. Here I wanted to stress that the word detects means that this quantity that I'm showing on the top of this page vanishes on the horizon and only on the horizon, switching its sign on that region. And so it does not provide any false positive. Then the next question is if we can do something better from a practical point of view. And in our paper, we said yes, because we can construct also another quantity, which is called the Cartan curvature, which can detect the horizon. However, there are at least two practical improvements. In fact, these appropriate Cartan curvature are first-degree quantity, and so they are much less expensive to compute when dealing with the numerical computations. Furthermore, they are foliation independent. Then we have tried to investigate what happens in lower dimensional gravity. In lower dimensional gravity, there is no Weil tensor, and the first consequence is that black hole solutions can only exist for a negative cosmological constant. Therefore, we have tried to identify the appropriate scalar polynomial curvature invariants and the appropriate curvature invariants which detect the horizon for the BTZ black hole. And indeed, we were successful in our job, but we have noticed one really important consequence of lower dimensional gravity. In fact, we were able to detect the horizon using these techniques only for non-vacuum space-time, and so only when there is an electric charge in the black hole. However, in 1+3 gravity, these techniques worked also for vacuum space-time, such as Schwarzschild and Kerr. And this is indeed, according to us, an important difference that we have.
Nearly, you have 3 minutes left.
Okay, in this context, we had in mind a different physical application. In fact, ADS-CFT correspondence can be used for studying strongly coupled systems, such as quark-gluon plasma. And in this case, we can use high-resolution shock capturing methods for numerical simulations. However, also in this case, it is necessary to remove causally disconnected regions and therefore to identify in the most convenient way the horizon. Then the last application of my method I want to discuss is how to find the horizons in the McWitty spacetime. This spacetime describes an evolving black hole inside an expanding universe. Therefore, in this case, the mass of a black hole is evolving in time, generalizing the swatched anti-de Sitter solution. So in this other paper, we have written down the cosmologic equation for the evolution of this Friedmann equation, and in particular, we have focused our attention on some cosmic fluids, which are some sort of unified dark matter, dark energy proposal. Then in this case, the algebraic equation for locating the horizon is a third-degree equation, which depends on the time evolution of the Hubble rate. And we have identified some interesting patterns. We have shown that there can be 1 or 2 relevant physical solutions to this equation. So we can have a cosmological horizon and also an event horizon. However, the cosmological horizons exist regardless of the type of matter content of the universe we are considering. Instead, the event horizon can only exist at some appropriate time interval and only when you are considering some type of matter content. In particular, this existence or non-existence of the event horizon depends on some non-trivial relationship between the Hubble function and the Hawking-Hayward quasi-local. And this qualitative prediction are independent on the modeling of the cosmic fluid that we have applied. So let me summarize. In our research, we have investigated a local method for locating the black hole horizon because general relativity is a local field theory, and also because it is important when doing numerical simulation, which are required to apply the excision method. In particular, we have used 2 methods, one based on scalar polynomial curvature invariant and another one based on Cartan invariants. And we have seen that some appropriate curvature quantities vanishes on the horizon and only on the horizon. We have discussed some specific example both in 1+3 and in 1+2 dimensional gravity, and we have clarified the role of the wild part of the curvature. And at the end, getting back to general relativity, we have also applied this method for finding the dynamical evolution of the event horizon and of the cosmological horizon in the McWitty solution. And this is all.
Okay, thanks, Daniele. If there are questions.
Yes, I see one question in the chat. So, indeed, the event horizon is non-local and it's a teleological quantity. We didn't want to consider isolated or killing horizon because it will be the same conceptual problem. So this method dealing with curvature quantities was for making compatible the locality of general relativity, which is one of its basic properties, with the event horizon that this theory predicts.
Zurab, excuse me, are you online?
Yes, I'm online, but I don't
Yes.
understand.
I think there are no more
There are
questions.
no more questions. Okay, then we continue. Right.
Okay, thank you.
Okay, thank you. So next speaker is Mohammad Sharif about compact strange objects in modified gravity. Given that in non-modified gravity we already know everything about compact strange objects. Please, we see your screen.
Yes.
You can start.
Thank you very much. So I'm talking about some strange objects in Brans-Dicke theory. Here is the composition of the universe mass. That this part of the universe is visible, but these two parts, 23% dark matter and 72% dark energy, are invisible. So in visible parts, you can see that 0.5% are the stars. So I'm studying here about the strange stars. Well, stars can be classified by their size, mass, luminosity, and color. In particular, neutron star, when the collapsing star core at the center of supernova contains mass between 1.5 and 3 solar masses, the collapse continues until electrons and protons combine to form neutrons, producing a neutron star. Well, gravitational pull is balanced by neutron degeneracy pressure. Neutron stars are the most dense object after the black hole. Even a cubic meter of a neutron star would weigh around 400 billion tons. Quarks are the building blocks of other particles. These are confined particles. They never found in isolation. The energy spent to separate quarks gives rise to new quarks. You can see from this diagram that these are quarks. They are lying in pair, but when we spend some energy to separate them, new quarks are produced, but they are also in pair. Well, there are 6 types of quarks known as up, down, strange, charm, top, and bottom. Up and down quarks have the lowest masses of all quarks and generally stable. Strange, charm, bottom, and top quarks can only be produced in high energy collisions. Quark star is a hypothetical compact star. Protons and neutrons deconfine in the core of a neutron star due to high temperature and extreme pressure, leading to a bath of quarks. Density is much higher than a neutron star. Masses of quark stars lie between 3 to 5 solar masses. Some words about the massive Brans-Dicke theory. The very well-known Dirac postulate that relationship between ratios of size scales in the universe to that of force scales, which yield very large dimensionless numbers. Hubble discovered that the farther a galaxy is, the faster it recedes from us. So this gives the idea of expanding universe. Combining these two, we found that gravitational constant is not a constant, but varies with the time. So this concept was used in Brans-Dicke theory. In 1961, Brans and Dicke introduced a scalar tensor theory by representing the reciprocal of varying gravitational constant through a massless scalar field. The scalar field is coupled to matter as well as gravity through a coupling constant denoted by omega BT. Okay, now low values of coupling parameter are used to describe cosmic reflection. For weak field situation, the value of coupling parameter must be greater than 40,000. And deviations from GR are insignificant. To avoid this issue, massive Brans-Dicke theory was introduced by introducing a scalar field, massless scalar field. So for this, by introducing massive scalar field, the action for this theory is given here. Corresponding field equations are given in this equation, where wave equation is here, and the corresponding terms you can see here. Now we can discuss some properties of compact objects. First, the equation of state. This is the relation between state determinants like density and pressure. This characterizes the state of matter under a given set of physical conditions. The very well-known equation of state to describe the compact object is given by MIT Bag model. Here, PR is the radial pressure, rho is the density, and B is the Bag constant. Different values of the Bag constant represent different scenarios. We can have the value of Bag constant for massless strange quarks between 58.9 to 91.5 MeV, but for massive quarks, this lies between 56 and 78. Another well-known quantity is the gravitational redshift. This is given by this expression for compact object, and its limit is found to be less than 5.211 in this paper. And mu is the compactness factor, and its limit is given by must be less than 4/9, which is verified in this paper. Now we see that stability of a body is the property which causes to develop forces that restore the original condition when it is disturbed from a state of equilibrium. You can see in the two figures that this is the state of instability because we cannot have stable position after disturbing it. But we can have stable position even after its disturbance. So this is the stable situation. Well, we can have many ways to check the stability of a compact object, but I'm here mentioning the three well-known. First is the causality condition, the second is the Harara's cracking approach, and third is the adiabatic index. Causality condition, this is in fact is found by the speed of sound, which must be less than the speed of light. And Harara's cracking approach
5 minutes.
This appears when the radial, okay, I'm skipping the details, and its condition is given here, and condition is, its limit is given here. Okay, we have to use the junction conditions to discuss the compact objects. And for physical acceptability, we must have the Petri coefficients positive and monotonically increasing. Also, the physical parameters must be maximum at the center and monotonically decreasing towards the boundary. The third condition is radial pressure must be 0 at the boundary. So these are the physical conditions, and the anisotropy must be 0 at the center. Further, the energy conditions must be satisfied. Now we take a static spherically symmetric line element, and the energy momentum condition, the energy momentum tensor is the isotropic fluid. When we impose the Karmarkar condition, we have this differential equation, and its solution is given by this expression. Here, A and B are integration constants. Okay, when we apply the MIT equation of state back model, we can have the from the field equations pressure and density, and the wave equation with potential. We discussed the wave equation for 3 star candidates with m phi is equal to 0.001. Okay, we assume 2 types of solution and find another one. For the first solution, I'm giving the details for the first solution. The second one will be follow it. Okay, when we use the first temporal component can be obtained as follows. Here, the constants can be found through the matching conditions. These are given here, A, B, and small b. And the condition that pressure, radial pressure must be 0 at the center gives the back constant. Okay, now we can see from the table that we can have for 3 star candidates mass, radius, and equation state parameter, and we can deduce the back constant. And from here, these using, we can find the rest of the parameters. Okay, now we can see the graphical analysis that metric potentials, it should be positive, and it is coming positive from our solution, that it is increasing for the 3 star candidates. Similarly, you can see that energy density and radius pressure, as well as transverse pressure and isotropy for this solution, giving a viable solution. Dominant energy condition is also satisfied. We can also see for the stability that radial velocity, initial velocity, and adiabatic index lie in the required limit. So this means that we have found stable situation in this case. Similarly, we can have the mass, compactness factor, and redshift parameter in the required limit. On the same lines, we can discuss the second solution, but I'm not giving the details. Instead, well, we can find the constants through matching conditions, and this is the back constant. And again, table for this solution and this graphical analysis. We also have the same situation that metric potentials are positive. Energy density, matter variable lie in the required limits. Dark energy, the dominant energy condition is satisfied, and rest of the quantities lie within the required limits. So we can conclude that we have computed 2 anisotropic solutions by using MIT back model in the background of massive Brans-Dicke theory. We have seen that the graphical analysis indicates that energy density and pressure decrease towards the boundary for both models, which is the required for physical implications. All predicted values of the back constant lie within the required limit. The positive anisotropy within stellar models implies the existence of an outward directly repelling force acting against the force of gravity. The constructed models are viable and they satisfy all the energy conditions. Similarly, the behavior of gravitational mass, compactness fraction are consistent with the Buchadal criteria. Similarly, redshift parameter and causality condition, these are all satisfied. So we can conclude that the stellar structures obeying MIT back model in the background of massive Brans-Dicke gravity satisfy all the required conditions and can be treated as a viable as well as stable models. Thank you very much.
Thank you. So if there are questions, please, you can write on chat, if any. So I don't see questions. So thank you, Muhammad, once again. So we can go to next speaker.
Thank you.
Partha, Sarathi, Majumdar, about holographic bound on area of compact-binary-merger-remnant. Okay, it's visible now. You can also switch on your cameras. Microphone.
Yeah, can you hear me now, please?
We can
Hello?
hear. You can switch on also your camera. I think we will see also you.
No, I would rather not switch on my camera because my connection is not very good. So if you permit me.
Okay, then continue.
Okay, but can you see my screen?
Yes, we can see your screen, so you can go ahead.
Okay, good. So let me begin now. So this is about GW150914 basics. This is something very familiar because all of you have probably seen the signals from the Hanford and Livingston data put forward by LIGO and how they combine beautifully after a shift. On the right-hand side, we have an old fact sheet from gravitational wave 150914, where they're confident that the two in-spiral binary components were black holes of mass 32 to 41 and 25 to 33. Now, these numbers have changed a lot, but what probably has not been confirmed yet is the following. Even though GW150914 results are consistent with both in-spiral and remnant configurations being black holes, yet there is no evidence of a horizon from either the in-spiral components or the post-ring-down remnant. There's also no evidence of accretion from either the in-spiral components or the post-merger remnant. So in fact, one is missing what one would call a smoking gun signal. And because of this uncertainty has spawned a huge literature on black hole mimickers. They fall into various categories: wormholes, boson stars, gravastars, fuzzballs, etc. And they have been beautifully reviewed by Vitor Cardoso and Paolo Pani in this Living Reviews last year. So there are two issues that come up from this case. How do we distinguish these exotic compact objects, which do not have a horizon, nor do they have a singularity, from black holes, which of course have both? There's also this question which I am posing: are there theoretical predictions which will work for both classes, namely both for the ECOs as well as for the black holes? And this is what I wish to answer in this talk. Well, before I get to our paper, what I want to talk about is another contribution last year by Adazi et al., where they asked the question, how compact can ECOs be? And here they appeal to the hoop conjecture given by Kip Thorne in 1972, which said that there exists a critical closed surface of revolution if you rotate a circular hoop of radius equal to the Schwarzschild radius. Of course, all the compact objects we considered have a Schwarzschild radius. So the question is, if they become so compact that their actual size becomes close to the Schwarzschild radius, then it's very likely that they will collapse to a black hole. So there could be a gravitational instability of the ECOs. This is the contention of the paper by Addazi et al. This is like saying that adiabatically an accreting ECO without reducing its compactness may collapse to a black hole. Now this paper is very nice because it tells you that maybe there is an instability which does not protect these other ECOs, and they all collapse to a black hole. However, from the data, there is no information on accretion of either the binary in spiral or the post-merger remnant in GW150914 and all the subsequent so-called black hole mimickers data, which has now been accumulated by LIGO and Virgo. Okay, so the question is, can we say anything more? So the paper that we wish to present here was done by Anaria Ray and myself. It's appeared in the archives very recently. We find a lower bound on the area of post-binary merger remnants. Now we know this from the black hole area theorem that if both the in spiral and remnants are black hole, then there's an increase in area. There appears to be some agreement with observations, which I have listed here, the references. But what if the remnant is not a black hole? We don't know for sure because there's no smoking gun signals. And we approach this question based on two very well-known hypotheses. The generalized second law of thermodynamics, which is enunciated by Bekenstein in 1973, and the entropy bound, which was also enunciated by Bekenstein, but it is tightened by loop quantum gravity corrections, which Ramesh Kaul and I found in 2000. Together, these two would imply that there is a lower bound of the cross-sectional area of the remnant of a binary black hole coalescence. So what does the generalized second law say? Well, we know this. Basically, it's valid in a situation where matter falls into a black hole, such that the entropy outside the event horizon, the thermodynamic entropy, actually decreases. Of course, this is not valid. This is not a valid situation if there is a second law. This also defines that the black hole itself must carry an entropy, which is a function of the horizon area, in order that it could be compatible with Hawkins' theorem regarding the area increase in black hole coalescence. In that sense, you could think of this one as a generalization of the classical area theorem for black holes, where the area is now replaced by entropy. And therefore, if we can compute the entropy in any quantum gravity framework, because only quantum gravity will explain or will underline the construction of black hole entropy. There is no such thing as semi-classical or classical black hole entropy. Only in that case does this generalized second law really come into force. So when two black holes coalesce into a final configuration, the final entropy must be bigger than the sum of the individual black hole entropies. However, if the remnant is an ECO, in addition to producing an ECO, there will also be gravitational waves. So the final entropy will be sum of the gravitational waves plus the ECO entropy, and that must exceed the sum of the black hole entropies. Now, what we know is that we can actually compute the black hole entropy ab initio in loop quantum gravity. To do that, we go beyond the idea of the event horizon. We generalize it after Ashtaker to talk about isolated horizons, which is a null inner boundary, which is a marginally closed trap surface. Of course, Einstein's equations hold on this surface. So it's a null inner boundary of space-time, and therefore it has a local description. But because it's a null inner boundary, the induced metric on the isolated horizon must be degenerate. And because it's a degenerate metric, there is no inverse of this metric, which means only a certain class of field theories can be written down on this three-dimensional null hypersurface. And these must be topological in nature. They must not involve the non-existent inverse of the metric. Now, in 3 dimensions, in the context of 4-dimensional loop quantum gravity, the degrees of freedom have to do with connections and their corresponding canonical conjugates. The connections here are gauge connections, and therefore the degrees of freedom on the isolated horizon would be the geometrical pullback of the gauge connection appropriate to space-time. Now, if you take this kind of a pullback, what you get on the isolated horizon is a Chern-Simons theory. That, of course, is a topological field theory with the coupling constant being given by the area of the horizon divided by Planck area. In the quantum theory, sorry?
4 minutes.
Sorry? 4 minutes. Okay. Yeah, all right, fine. In the quantum theory, of course, this is realized as a quantum Chern-Simons theory. The Chern-Simons theory is coupled to the spin network, which describes bulk quantum gravity in the loop quantum gravity formulation. Now, because I have no time, I shall quickly go over this. You can count the Chern-Simons states by looking at the conformal blocks of SU2K Westover-Norwegian model, and this is an exact calculation for large values of K, which corresponds to macroscopic horizons. And using the fusion rules, you have this long formula where we have the sum over M, the azimuthal quantum number, over going from minus J to J. I runs over the spins in a particular puncture. Then we sum over all possible spins and all possible punctures. This is holographic because we're actually counting the entropy of a 4-dimensional black hole from the conformal blocks to 2-dimensional Westover-Norwegian model. And what we get is not just the Bekenstein-Hawking area law, which is right here, but you get also a whole series of infinite corrections, starting with a law with a unique coefficient, and every term in the series is actually given completely calculable and finite. So that's what we mean by holographic correction. So now if you have the entropy bound, as I said, the entropy of the ECO is bounded from above by an entropy of the area, of entropy of the black hole whose horizon area is this. Now let me skip this and quickly go to the fact that this means this particular inequality would be satisfied. And this inequality holds irrespective of whether the remnant is a black hole or ECO. So you can rewrite this inequality in various ways, and you can actually estimate, because the entropy of the gravitational wave can be calculated from the data. And of course, you know, if these are black holes, if the in-spiral is a black hole binary, then you know what the areas are, and therefore you can actually find the lower bound from the GW150914 data. But what if the binary in-spiral is not just a black hole? Does this bound generalize? So if we now imagine that the boundary in-spiral consists of binary in-spiral consists of components which are ECOs, then you see the entropies of these quantities also obey a bound, so this inequality holds. But does this mean that this is true? Well, this is not necessary mathematically, but it's sufficient. And it's necessary from a physical perspective if the bound has to work for in-spirable black holes, as it must. So the bound that we find, the lower bound on the area, is actually independent of the actual configuration of the in-spiral as well as the remnant. So you can rewrite this by defining the compactness ratio like so. Now, I don't have much time to talk about gravitational wave. Maybe I have 2 minutes. Zurab, do I have 2 minutes? Zurab, hello? Do I have 2 minutes? Hello?
Yes, please, 2 minutes.
Yeah, 2 minutes. Yes, please. Okay, so here we follow the method of coincidence probability of recurrence of trajectory, which was championed by Shankeng Ma, a Chinese statistical physicist in 1984. I don't have time to talk about it, but in this case, what we can do is, if we know the Fourier spectrum of the gravitational waves in, let's say, 150914, we can then compute it.
Yes, for questions. If you conclude one question, 1 minute will remain for questions.
Yeah, okay, fine. I'm
okay,
concluding.
Go ahead.
Yeah, please, thank you. So we have this final formula, which I have no time to explain, but you can see my paper, the one I have referenced earlier. And indeed, here what we have done is to take the coincidence trajectory by replacing it by coherent modes of gravitational waves. So we have a formula which works, and now the results. Okay, so now you can calculate the equilibrium entropy of the gravitational waves, and it turns out to be order 50 in units of the Boltzmann constant. And rather than say what these are, you can read them, or you can see the diagrams. So here we plot M1, and we plot the lower bound as a function of area of M1 and M2, the two black holes. So this is in the case when the compactness ratios are unity, which is for the black hole case. And we have another result, which is the case for non-black holes, where we actually plot the lower bound and the compactness ratio as a function of the two compactness ratios. So that's it. My conclusions, since the inequalities are insensitive to the precise nature of the in-spiral or remnant configurations, we may have wide applications for interference experiments like LIGO, Virgo, and others. The results cover a range of estimated masses for most recent black holes, including GW 1905-21, and so we may make some predictions. Of course, the unsatisfactory feature of the entire work is that we took the generalized second law and the entropy bound as hypotheses. It would be nice if we can come to some proof on the basis of quantum gravity. Thank you very much. Thank you very much. My talk is over. Hello?
Okay, thank you. There is one question.
Yes, please.
From Ivan Suso. What about the ring down signal, that for exotic compact objects should be different from the black hole inspired?
I should answer by saying that both the in-spiral binary as well as the remnant I've considered are in equilibrium configurations, which means that we are considering the situation far away from the transient when the black holes or whatever ECOs they are in the binary and spiral tend to get to be close to each other. That, of course, is a situation where the entropy can no longer be calculated using equilibrium methods. We are fixing our attention to equilibrium configurations.
Okay, so thank you. I think we can go to next speaker, which is Sobhan, Kazempour, Ishka.
Yes, I'm here.
Reporting gravitational wave constraints on the Einstein-Gauss-bonnet cosmology. Please.
Right. Problem with the screen.
We see your slides.
Okay. Can you hear me completely?
Yes.
Okay. Initially, I would like to thank organizing committee of Zeldovich meeting for this opportunity. As it's clear, my name is Sobhan Ishka, and my supervisor name is Dr. Amin Rezai. In this presentation, I would like to talk about imposing gravitational wave in Einstein-Gauss-bonnet theory. First of all, I would like to say that about this presentation. This presentation includes motivations, introducing the theory, field equation, gravitational wave, a constraint, and summary. In this slide, I would like to talk about our motivations for doing this research. As it's clear, and all of us know that the accelerated expansion of universe has observed by several cosmological data such as type 1a supernova, CMB, and large-scale structure. So the dark energy has been introduced as an unknown form of energy in order to explain the accelerated expansion on the largest scale as one of the theories and solutions. I would like to add that one of the valuable solutions in modified gravity theory is scalar tensor theory, and it can explain the accelerated expansion of the universe. and they can solve some problems, and it was successful for solving some problems and fundamental problems, especially evaluation of early universe. However, there's a problem, for example, in the speed of gravitational wave. This theory is not agreement with some data. So we decided to extend this theory, scalar tensor theory, by Gauss-bonnet term, and we added it to this theory. Moreover, I would like to add that the Gauss-bonnet theory is one of the most important theories, and there are some successful in this theory and can solve several fundamental questions in this theory. It should be noted that we prefer to use the nodal symmetry approach in order to solve this theory, because with use of this approach, it would be possible to select some constant, and or system can be simpler. In the next slide, I would like to introduce our theory, the Einstein-Gauss-bonnet theory, and you can see that this action here. As I mentioned before, this action, the scalar tensor action, is extended by the Gauss-bonnet term, and you can see that the Gauss-bonnet term here. Moreover, there is a coupling function here, as you can see that, and it should be very important to say that if we in the 4 dimensions, if we consider f as a dimensionless coupling constant instead of coupling function of a phi, the Gauss-bonnet term does not contribute to the gravitational dynamics. So the reason of this issue lies in the fact that the Gauss-bonnet term, the Gauss-bonnet invariant, is a total derivative. So we consider the coupling function. As you can see that the LM is a matter Lagrangian, which consists of 2 parts, the standard material and the interactive expression. And the VFE is a scalar potential. For this theory, we consider a flat universe, and we consider the FRW universe, and you can see that metric. And in the next stage, in order to calculate the field equation, we use the integration by parts, and we convert the second derivatives, the terms, into the first derivatives. So we calculated the point-like Lagrangian, as you can see that here. And in the next stage, we draw with varying respect to the scalar field, T, we calculate and achieve the equation of first equation of motions for this Lagrangian. In the next stage, with varying respect to the metric, we calculate this equation and general equation, and we indicated the 0,0 component of this equation and the first 1,1 component of this equation. It is worth pointing out that with use of this field equation, we can analyze the cosmological evaluation and all the things which is related to this theory completely. However, because the time is limit, I want to disregard this explanation. And I want to introduce the gravitational wave constraint can be used in imposing some constraint or any modified gravity theory. And you can see that with use of these 4 main tests, which there are in gravitational wave, we can constrain the gravity theories. And the first one is standard sirens, and the second one is gravitational wave speed. The third one is gravitational wave damping, and finally additional polarization. In a standard sirens, as you can see that the standard sirens is proportional, inversely proportional to the gravitational wave luminosity, and the equation of this issue, the equations of these issues and the formulas, you can see that in these forms, and it should be considered that, and we can point out that with use of the distance, gravitational wave luminosity distance, and with use of with mixture of another method which I mentioned here for light source at the.
You have 3 minutes left.
Okay, we can use of the standard filing. However, I want to speak about gravitational wave speed that I believe that is much important in comparison with the other method. As you can know that in gravitational wave in modified gravity do not travel as in GR, and there is some differences in, and you can find parameterized the generalized provocation here, and the G mu is effective metric, and MAG is a mass of graviton, and I want to talk about it in the next slide, and the other thing you can see here, and I want to point out that the mass of graviton, it can change the propagation of speed, gravitational wave speed, and there is several bounds about this issue, and you can see that the present bound from the LIGO Virgo here, the value of this gravitation, the mass of graviton, and the mass of graviton could be calculated in a different several modifier of gravity, and we could compare this value with the data have been detected, and we can constrain our theory with use of it. Finally, additional polarization is another things and another characteristics in gravitational wave we can consider in order to imposing some constraint on modified gravity theories. It is clear that in GR there are two tensor polarization, H plus and H cross. However, there are the most general expression, this type of polarization. For example, in scalar tensor theory, there is a some mode, and it's different in general relativity, and in massive gravity there are two vectors, and you can see that this is different and a scalar one. With use of these things, we could constrain our theory in the best way. In summary, I should like to say that I explained our motivation for this investigation. I introduced the Einstein-Gauss-bonnet theory very briefly. I show some of our calculation, the field equations of that theory, and I introduced some characteristics in gravitational wave we could use in order to imposing some constraint our theory. So you can see my references. Thank you very much for your attention. That's it. My presentation is finished. Can you hear me?
Yes, Sobhan, thank you very much. Zurab, I didn't hear you. Maybe we can move to the next speaker, who is Andrey Mayorov.
Thank you very much. Bye.
Thank you. Apparently, there is some technical issue with the Zurab, so it's Gregory Berezhiani. I will keep running this session. Andrey Mayorov, can you hear us? Can you please activate your microphone?
Yes, I can. Can you hear me?
Yes. Please switch on your camera. Yes. You can start, please.
Just a moment. Okay. Good afternoon. My name is Andrey Mayorov, and I'm from Moscow Engineering Physics Institute. I'm going to talk about the antiparticles and cosmic rays, and mostly I will speak about the antiprotons because I am limited in time. I'm a member of Pamela collaboration, and I'm going to present an updated results in measurements of antiprotons in cosmic rays. So, of course, this talk is significantly different of the most talks we listened before, but in any case, I will start. Why it is interesting to measure the antiprotons in cosmic rays? There are different reasons why we try to measure these antiparticles in our space, in our cosmic rays. First of all, we try to understand the properties of the interstellar medium because of the most antiprotons, according to our assumption, has a secondary production. So it's very interesting to understand how these particles produced near the sun in our galaxy. Of course, we are interested in antiparticles, also in antiprotons, because of some theories which give us some information about the existence of antimatter domains. Maybe antiprotons here not the best probe to check the existence of such forms of antimatter, but in any case, it also will be very interesting. Especially, it was very interesting expected 20 years ago. Then these works was very popular. And finally, we're looking for antiparticles in cosmic rays because of dark matter. Dark matter, according to our modern assumption, also can be unstable, or it can annihilate, self-annihilation. And in these processes, the positrons, antiprotons, or even antineutrons or antihelium can be produced also. So it's very interesting to understand which flux of these antiparticles can be associated with such kind of exotic additional sources. A few years ago, in 2020, the precise measurements of antiproton to proton ratio was presented by the Pamela collaboration. Here you can see the dependence and energy dependence on the antiproton to proton ratio. The red points are the Pamela results, which was obtained using the information collected on the near-Earth space from 2006 up to 2009. Of course, from the first point of view, it looks like that all the antiprotons has a secondary production, but at high energies, especially more than a few dozens of GeV, you can see that the antiproton to proton ratio is approximately a constant. It means that the spectra of antiprotons looks like a spectral index of protons. It means that the protons and protons must have the same origin. But we know that the antiprotons can be produced in significant number in supernova explosions. According to our modern assumption, the antiproton spectrum must be softer. So here you can see the dotted lines. These lines was obtained during the calculation of the secondary production antiproton flux. And here at the same picture, you can see the dashed line. This dashed line is the sum of the secondary production and additional source. According to these results, we can conclude that the most of antiprotons has the secondary origin, but we can expect that some number of antiprotons, especially at higher energies, was born at additional sources. It may be the known astrophysical sources of different kinds, or it may be the exotic kinds of the matter, like annihilation or decay of dark matter particles. A few years ago, in the next level experiment called AMS-02, the PAMEL results was confirmed. You can see here the antiproton to proton ratio. This is kinetic energy measured in these two experiments. The blue points is the PAMEL measurements, and the black points is the updated AMS-02 measurements. You can see here also the flatness of the antiproton to proton ratio. So these data are in agreement, and we see surprisingly hard cosmic ray antiproton spectra. Here you can see also the different kinds of calculations of the secondary antiproton flux. For example, here you can see the uncertainty due to uncertainty in the antiproton flux and this ratio due to our problems, our not clear understanding called the cross-section production of antiprotons, some uncertainties with the propagation, connected with the propagation of antiprotons in the galaxy, in the interstellar medium, some uncertainties due to primary slopes, and uncertainty connected with solar modulation of cosmic rays, but solar modulation connected mostly with the lower energy below the 10 GeV. So from this point, the scientist has two different points of view. There are a lot of publications which conclude that all the antiprotons has a secondary production, but some kinds of scientists think that we have some additional source of antiprotons in cosmic rays. So I will skip this slide. I want to remember that the PAMEL is the space-borne experiment, which was operated on the near-Earth orbit from 2006 up to 2016. So we are going to improve the statistics and extend the energy range. We try to improve the statistics and extend the energy range of our measurements because we have some possibilities to do it, to improve our results and try to obtain some new information about antiprotons, especially at higher energies. So by my group was done the next analysis. We use some updates of our analysis. For example, we update the basic selection criteria of particles to improve the statistics. So we improve our simulation software to be more assured that our antiprotons are really antiprotons and not the background. We take to analysis modern machine learning techniques, improve the spillover study. So we try to exclude the mistakes in our SIGN measurements up to higher energies. And we try to improve the efficiency study to be sure that our measurements of the spectral index is correct and that doesn't depend on some experimental technique problems. And of course, we're taking to analysis all the information which was collected from the beginning up to the end of the flight of the experiment. So here you can see the evidence distribution via deflection, which we measure with our technique system. Deflection is the inverse rigidity. So we have collected 2 times more antiprotons when it was before. And we can see that between the antiprotons and so-called spillover mistakes in our measurements of the rigidity, we can see here the gap. So we can conclude that the background from the spillover into protons is negligible up to approximately 700 of GeV. So here you can see some examples of our events. At the top of this slide, you can see the annihilation of the particles which stopped into our calorimeter, the classic annihilation of the matter. So here I want to show you our results. At this slide, you can see the preliminary updated antiproton to proton ratio versus kinetic energy. Here you can see the comparison with our previous publication in 2012. This which is shown here by black points, and updated results are shown here by red points. So because we are improve the statistics by 2 times, we have put here more points with the same error bars as it was before, and we extend our energy range up to 600 GeV. And at the last point, from 400 up to 600 GeV, we can put here an upper limit. So it means that we can't find antiprotons at energy level more than this upper limit. So first of all, we must think here how to choose the energy binning at high energies to be more to obtain more.
Andrey, your time is over.
Yeah. Okay.
Your time is over.
My time is over. Okay. So I've shown the final results. My conclusion is that so we obtain new results, updated results. The main question here now is not the flatness of the antiproton to proton ratio, because it is so. Now the main question is, what about the secondary particle calculations, secondary antiprotons production cross section? So this is the main question now, to be sure that this is all secondary particles, or we have some additional sources. So thank you. I have 10 minutes only, so my time is over.
Okay, thank you.
Thank you.
I don't see question.
Okay.
Okay.
Thank you very much.
So we go. Next speaker is Anastasia Kirichenko about anti-helium flux from antimatter globular clusters. Please, Anastasia, are you there? Try to share your screen.
Yes, I see. Do you see my screen?
Okay, we see it now. And we hear you. Please go ahead.
My name is Yes. My name is Anastasia. The topic of my work is cluster of pointing stars as the sources of antinuclear in a stream of galactic cosmic rays. At the end of the 20th of last century, Zurab predicted the existence of antiparticles. Scientists began to study antimatter, and according to modern concepts, it has 3 possible nature of origin. Primordial antimatter, it could be created in the early universe as a reflection of non-homogeneous barosynthesis, evolved in antimatter domains, and now it can exist in the form of macroscopic antimatter object, like a globular cluster of antimatter stars. Secondary antimatter, it formed as a result of solution and nuclear component of cosmic rays with interstellar gas or with supernova shell. Antimatter from exotic sources, this is evaporation of primary black holes or decay and annihilation of hypothetical particles or dark matter. Baryonic asymmetry of the universe, it's observed predominance of matter over antimatter in the visible part of the universe. As Sakharov and Kuzmin formulated the necessary conditions for barosynthesis, asymmetry between particles and antiparticles as a violation of charge and combined symmetries, violation of the law of conservation of branches, and violation of local thermodynamical equilibrium in the early stages of the formation of the universe. If barosynthesis is non-homogeneous, it may lead to antibaryon excess in some region, and this primordial antimatter is interesting for this work because the objects hypothetically consist of primordial antimatter could be preserved in the halo of our galaxy. An astronomical object smaller than a globular cluster cannot be formed surrounded by matter during cosmological evolution. With smaller size, antimatter would annihilate with matter before the galaxy formation. The larger size of the domain is constrained by the observed fluxes of gamma radiation. The effect of the existence of a globular cluster of anti-star can be registration of antinuclei or the creation of a limit of their flux in the birth IMS-02 from our experiments. We based our analysis on the symmetry of the physical laws of object and of matter and antimatter using the knowledge that we have about globular cluster. We can predict the properties of the cluster of anti-stars. Globular clusters are located in the halo of galaxy and contain more stars of much older than open globular clusters than in the disk of the galaxy. They usually consist of stars that have a lower proportion of elements heavier than hydrogen and helium. The illustrations show the distribution of globular clusters in our galaxy. The position of the Sun is indicated by a cross. Using information about the known observable globular cluster M4, we assume that it is a candidate for globular cluster of anti-stars. Based on astronomical observation and general theoretical model and evolutionary structure of globular clusters, we are interested in mechanisms of injection of antimatter into cosmic rays, so that we can draw a conclusion on predicted anti-helium fluxes. Consider possible mechanisms for injection of anti-helium into cosmic rays from the globular cluster M4. The stationary flow of matter from the surface of anti-stars, stellar wind. Anti-stars lose part of their mass constantly, create a large concentration of antimatter from globular cluster. But it should also be noted that this is low energies. Flare of anti-stars occur more often than anti-supernova explosion. They are less energetic, and characteristic energies for this process is a gap range. Anti-supernova explosion occur less often than flare of anti-stars, but they have advantages in realized energy from such processes. That is why anti-supernova explosions may be most likely sources of antinuclear and galactical cosmic rays. But important to take account of background events such as secondary antimatter. Figure 2 shows a calculation spectrum for secondary antiparticles of antihelium, antideutron, and antiproton. Please pay attention to how small the value of antihelium fluxes are. To register secondary antihelium, you need to go down to the level of sensitive from 10 to the power minus 12. If the IMS-02 will register antihelium nuclei at sensitive level higher than secondary ones, then registered nuclei will be from primary sources, for example, from a globular cluster or from exotic sources. The analysis of the work begins with a calculation of the injection of antistellar wind, because globular clusters are massive objects in the galaxy. In order to understand whether antimatter leaves the limits of the cluster, the stellar wind velocity and the second cosmic velocity were calculated. Comparing the results, we can conclude that antimatter actively leaves the cluster already at the stage of stationary flow of matter. Then all three of mentioned mechanisms in injection are theoretically possible. But it also doesn't guarantee that particles can reach the observed, I mean the solar system.
Anastasia, you have 3 minutes left.
Yes, thank you. Therefore, first of all, we consider the case of high energies because, as I already mentioned, this may be most likely injection mechanism since the magnetic field of the galaxy can prevent the penetration of low energy particles into the disk. 2 other mechanisms should be considered in future. The graph shows the result of numerical simulation of evolution of populations of globular class M4. In this graph, we are specifically interested in the number of neutron stars. Neutron stars are formed as a result of evolution of that. The number makes it possible to estimate of the energy density of antiparticles in cosmic rays. We use the formula for the energy density of cosmic rays of matter, substitute the variable below. Our numerical values are located in the table. As a result, we obtain the value 10 to the power of -4 centimeter cubed, and the cosmic rays energy density of matter comparison. For comparison, the calculated value does not contradict the experimental data for energy density of antiprotons. The next step it's necessary to simulate the motion of particles in the magnetic field of the galaxy in order to estimate the minimum energy of the particles penetration. The galaxy disk can conclude whether it was considered 2 other mechanisms. The task divided into 3 subtasks: development of program and for modeling particle motion, checking the correct operation of program, studying particles and solving equation motion. It starts from the first stage. We compile the function program with the input parameters of which are coordinate is the galaxy, and the output component is component of magnetic field in Cartesian coordinate system based on conclusion of the article which is listed below, which demonstrated an approximate model of the magnetic field of the galaxy. The calculation formulas for the magnetic field components is in the coordinate system presented on the slide. At the second stage, we check the correct operation of program. The slide shows the resulting topology from the program or to local field projection. And you can see the topology extends from a article nearby. It noticeable that the topology is almost concise, and we can conclude the program works correctly and can be used and simulate the motion of particles in magnetic field. Conclusion, I want to say...
Finishing.
Okay, thank you for attention. Then.
It's okay, go ahead.
Can you help me?
Conclusions. Yes.
How switch it? Help me, please. I don't understand.
You can formulate conclusions.
I have time yet?
Yeah, just you can say a few words about it.
Okay, I understand. Then continue. We considered the M4 globular cluster, which is hypothetically a candidate for the globular cluster of anti-stars in the galaxy based on symmetry of the properties of matter and antimatter. We studied the evolution of this globular cluster and mechanism of injection of antimatter cosmic rays. We calculate the energy density of antiparticles in cosmic rays in the case of high energies, and also check the operation of the program to simulate the motion of particles in the magnetic field of the galaxy. Further work is aimed to modeling the motion of particles in the magnetic field of the galaxy in order to estimate the minimum energy that a particle penetration into a galactic disk should have, and the end to obtain prediction of expected flux of antinuclear. Thank you. I finished and I need
Okay,
help.
thank you. There are no questions. And you can close full screen after your talk. And so you can escape. You can use escape.
Yes, I don't understand how to do it. Oh, thank you.
Okay. So now we see talk of Bikbaev about interaction of dark atoms with nuclei.
Can you hear me?
Yes, go ahead, please.
Okay. Can I start my show?
Yes.
Okay. Hello. Good day. My name is Bikbaev Timur, and the theme of my research work is modeling the interaction of dark or helium atoms with nuclei of baryonic matter. One of the fundamental physical problems of our time remains dark matter. If dark matter consists of particles, then they are predicted outside the scope of the standard model. Uncertainty in the choice of dark particles gave rise to a variety of theories that offer various objects for the role of candidates for dark matter. If we consider the scenarios of stable, hypothetical, electrically charged particles, then the problem arises of their absence in the substance surrounding us, since if they existed, they would have to be bound to ordinary matter and form abnormal isotopes, the content of which in the soil and water is subject to strict experimental restrictions. For various reasons, stable negatively charged particles can have only a charge -2. Let's call them O minus, or -2n in the general case where n is any natural number. In this paper, we consider 1 minute. In the paper, we consider a scenario of a composite dark matter in which hypothetical stable particles O minus form neutral atomic states of helium with primordial helium having nuclear interaction with baryonic matter and called dark atoms. Okay. An attractive feature of the helium hypothesis is that it includes only one parameter of the new physics, the mass O minus, which is approximately equal to 1.25 tera-electron volts. The helium hypothesis also provides the current density of non-relativistic matter. The most important thing about the helium hypothesis is that it can explain the conflicting results of a direct search for dark matter. Namely, the positive results in such experiments as Dama and Dama Libra, which come into apparent contradiction with all other experiments. For example, with such as CDMS and Xenon. The results of the Dama and Dama Libra
experiments can be explained by annual modulations of energy release during the formation of the low energy bound state of helium with nuclei. The problem with the helium hypothesis is that its constituents can interact too much with ordinary matter, which can lead to the destruction of the bound or helium system and the formation of abnormal isotopes. The existence of a low energy and the dominance of elastic processes in the helium scenario are based on the hypothesis of the presence of a dipole potential barrier in the interaction of helium with nuclei, which requires a correct quantum mechanical description. The aim
4 minutes.
Okay, the aim of the work is to build a numerical model of the interaction of the dark helium atom with the atomic nuclei in the framework of the proposed approach to such modeling to reveal the essence of the processes of interaction of helium with nuclei. A classical model is used in which the effects of quantum physics are successively added. First, the helium system was simulated consisting of 2-point bound particles, O minus and helium. A spherical coordinate system was introduced at the beginning of which there is an O minus particle, and around it on the surface of a sphere of the Bohr radius, an alpha particle moves stochastically at a constant speed. How the simulation was performed can be understood by the block diagram. Since an alpha particle in a coupled helium system has 2 degrees of freedom, the polar and azimuthal angles are taken as its coordinates. Through which, using the Bohr radius, the values of the components of the radius vector of the alpha particle R in each iteration of the cycle are calculated. Define the theta R changes in angles. Define the theta must satisfy the condition. At the end, the algorithm gives the trajectory of the alpha particle along the surface of the sphere of the Bohr radius. Define the theta are calculated by the following formulas. Here rand is a random number function that is continuous over a segment from -1 to 1. A condition on a block diagram is understood as a lower inequality. In fact, this is the inequality of a triangle on the surface of a sphere. This is the result of the algorithm. The figure shows the sphere of the Bohr radius on the surface of which the location of the alpha particle between the moments of time dt is marked with red dots. Before starting modeling the helium nucleus system, taking into account all the forces acting between the particles, the helium nucleus coordinate system was introduced, which you see in the picture. Coulomb interaction in the helium nucleus system. At this stage of modeling, we
you have 1 minute.
Okay, considered a system of 3 points interacting with each other by means of Coulomb forces, charged particles with the choice of coordinate system given above. The modeling process is clear from the block diagram. Before condition 1, the algorithm determines the value of the increment of the momentum of the alpha particle. The physical meaning of condition 1 means that the termination of the program algorithm, the excess of the kinetic energy transfer to the helium core over the helium ionization potential, which results in the destruction of the bound helium system.
Time is over, unfortunately.
And a helium system model was integrated into this model. In the figure, you can see result of the algorithm, namely the trajectories of the alpha particle and the particle minus.
Timur, your time is over. Your time is over. You have no more time.
Okay.
So I should quit your talk here. I warned you several times that you have to go to conclusions. So please, now you can switch off your screen and let the next speaker. Okay. You have no time for conclusions even, unfortunately.
Okay, conclusions.
Okay, so next speaker is Michael Wood. Please, you can switch on your, share your screen.
All right, can you hear me? Can you hear me? Great. So thank you.
Yes, please.
Thank you, Zurab. I really appreciate you organizing this. It's tight. I know this is the penultimate talk, so before we hear some recollections on Zeldovich, so let me just try to keep this nice and fast and to the point. My name is Michael Good. I'm at Kazakhstan, and this is some work done with collaborators Eric Linder at Berkeley, Yin-Chen Ong at Yangzhou University, and Robert Mann at Waterloo, and Frank Wilczek at MIT. So I'm going to talk about radiation from an inertial horizon. You probably don't know what I mean by inertial horizon, so let me give you a tiny bit of background. First off, let's consider the moving mirror model, which is a very simple toy model in 1+1 dimensions that radiates massless scalar particles, where we're going to impose a boundary condition such that it moves around in some arbitrary way and gives off light, just like black hole radiation. Now, the motivation here is simple. It's for its simplicity. A lot of the analytical things that we want to compute are computable. It's very fundamental. We don't have to worry about higher dimensions and curvature effects or superradiance or scattering. And the dynamical Casimir effect, which is a generalization of the moving mirror model, has been empirically verified. So there's a lot of hope here that the experimental data will tell us whether we're on the right track or not. So it's been known for 50 years that there's a tight correspondence between black holes and moving mirrors, but only in the last few years have we found that there's an exact correspondence between the radiation emitted by certain moving mirrors and certain space-time metrics. So a list of a couple of solutions are the Schwarzschild black hole, the Rising-Nordstrom, Kerr, de Sitter and anti-de Sitter cosmologies, and extremal black holes. So the Schwarzschild mirror is this red line here on the Penrose diagram. It goes off to an infinite acceleration in the far future. Now, if you turn the crank, plug it into the moving mirror model, you'll get a Planck distribution at late times. You can see it right here. The mirror has radiation that's at a temperature kappa over 2 pi at late times. For the Kerr mirror, we have two parameters, the mass and the angular momentum. But the mathematics is more complicated, but it can be done. Now, this is a pure Hawking effect. It does not take into account superradiance or backscattering. So, and all you need is a 1+1 dimensional moving mirror. You don't need to model the spherical asymmetry, which is quite a surprise and a significant conceptual leap. in understanding how the moving mirror model works. So this is a Kummer function, and at late times, it gives the correct temperature for Hawking radiation and also the correct limits in the Schwarzschild space-time. So the de Sitter mirror is super simple, in fact, very fundamental. It's eternally thermal at all times. It gives exactly the Planck distribution. The integration is quite difficult, but it is computable. The flux here is constant, as would be expected at equilibrium, where we have eternal Planck distribution particles emitted by the horizon here. So for the extremal mirrors, we get a nice little treat. Here, the extremal black holes correspond to the same spectrum from a uniformly accelerated moving mirrors at late times. There's no temperature. It's not in a Planck distribution. The temperature is undefined, and we get this Bessel function type trajectory spectrum. A here is the asymptotic uniform acceleration. So I just wanted to give you a little bit of background on that, and I think now that you know that there is a correspondence between mirrors and black holes, and that we can compute the spectrum and we can compute the energy, we are now in a position to look at what the hell is an inertial horizon. Okay, so for the black holes, as acceleration goes to infinity at some finite advanced time, we see that for the extremal black holes, it goes to some constant. Now, in the model, there are trajectories that can model the remnant and effervescence, complete evaporation, and here's where the acceleration goes to zero in the far future. So I might think this exhausts the possibilities for acceleration, infinite, constant, zero. But yeah, I'm good on time. But the idea here is that we can go to a zero acceleration at some finite advanced time, where now we're going to actually go to the speed of light to form a horizon, but the acceleration is going to drop off to zero. What is this moving mirror model? Well, here's the trajectory. It has this horizon at v equals zero. This is what it looks like in a conformal diagram. It touches down right at the horizon, this v equals zero line. And the energy can be computed with a Schwarzian derivative. We get negative energy flux at late times here past v equals -1. And the total energy, even though there's negative energy flux, the total energy is positive and completely analytic, inversely proportional to the mass parameter. So the spectrum can be computed analytically. We get a very big Mayer-G function. It's a very general mathematical function. All the known special cases are of our special functions are special cases of this Mayer-G, but this cannot be expressed in terms of our well-known function. So it's rich enough that we have some interesting characteristics of the spectra, but it is complex and deep enough that here, and simple enough that we can express it analytically. Numerically integrating over all the colors gives the same exact energy that we got from the stress tensor, so we know that the model is consistent. And just to kind of summarize it up in a nice table here, black holes have information loss with horizons, but they do not have negative energy flux or finite energy or finite particles. The extremals here have a horizon as well, but they have finite energy, meaning that their evaporation process stops. Remnants and the effervescence here don't have horizons, don't have information loss, but and they also have finite energy and negative energy flux. So this inertial horizon kind of fills a gap in the literature in a strange type of geometry that no one has considered before, such that we have information loss with this horizon, but we also have negative energy flux. And so we can imagine that this may have some interesting avenues to investigate with respect to the second law of thermodynamics. Perhaps you could open an oven shutter and collect this negative energy flux, cool it down the oven as the mirror jerks towards you, even though the mirror is moving away from you. So in conclusion, we have a trajectory and that hints at the possibility of a geometry that shines with negative Hawking radiation. And so for that, I thank you for your time.
Okay, thank you very much. I don't see questions, so we can go directly to next speaker. Thank you, Mike, once again.